All right. In this video, I want to quickly go over some of the key sources behind many of the ordinary differential equations that you will encounter, you will come across in your studies or your career. So let me write it here. Uh, some of the key sources, some of the sources behind ordinary differential equations that you will come across, you encounter in your studies. So obviously, one of the key reasons that you see ODEs in modeling real-world phenomena is this interpretation of the derivative. Remember, ODEs are those equations that involve the derivative of your unknown function, and your unknown function is a function of only one variable. And one of the interpretations that we have for derivative, when the derivative is derivative with respect to time, we can think of it as rate of change. This simple fact that the derivative with respect to time can be interpreted as a rate of change of the variable is the source of many of the interesting ordinary differential equations that you will encounter in your studies. So let me write that. Obviously, one main source of many of the ordinary differential equations that arise in modeling real world problems is the simple fact that we can interpret a derivative with respect to time as rate of change. So this is definitely one of the key sources behind many of the interesting differential equations that you will see. And we will see this in action very soon when I do specific examples of modeling. Now, another important source behind many of the ODEs that you'll see will be Newton's second law. Let me also write that. As we shall see, many of our ODE models, many of the ODEs of our ODE models, of these ODE models appear as a result of applying Newton's second law. In classical mechanics, Newton's second law of motion, Just as a reminder for everyone, the Newton's second law, what it says is that the net force applied to a body, which I'm going to denote by F, the vector F, equals mass times acceleration, right? That's what Newton's second law tells us. Remember, the main task in classical mechanics is to determine the trajectory the path of a particle, of a moving body. And let's, for example, consider the solar system. And let's say that you are interested in the path of each planet in the solar system. Or let's say that you're studying a rocket and you want to see the trajectory, you want to understand the trajectory of a rocket. So this is the main question in classical mechanics. You have a body or a collection of particles, and you are interested in the trajectories, the paths of these particles. And what Newton did is that Newton proposed a systematic method to deal with these problems, finding trajectories based on the formula that you see here. F equals ma. Remember, this F is the net force. Let me actually write this. The net force exerted on the body, applied to the body of interest, to the particle of interest, to the particle in whose path, whose trajectory is of interest to you, to a body. M is the mass, and obviously A is the acceleration, the second derivative of the position, acceleration. And then Newton gave us this like beautiful systematic procedure where we can use this formula in order to determine the trajectory of a particle, of a body, or a collection of particles. As a matter of fact, what Newton proposed, you can think of it as a three-step process. Every time you have a problem in classical mechanics, which involves determining the trajectory of a particle of a moving body, you just need to follow a three-step process. Let me also quickly go over that, because this is something that we will use in multiple of the models and several models that we will discuss later. So Newton proposed, let me write this, Newton proposed a three-step procedure, a three-step procedure to tackle the problem of finding the trajectory of a particle, to attack the problem of finding the trajectory, the path of an object, of a moving object, or collection of particles. The first step is that the first thing that you need to do if you want to apply Newton's second law in order to determine the trajectory of an object, which is, I think, the main problem in classical mechanics, is to choose a convenient coordinate system. Choose a convenient coordinate system with which you can label the points. Coordinate system. Cartesian coordinate system, or polar coordinate system, or in 3 dimensions, a spherical coordinate system, cylindrical coordinate system, and so on and so forth. Choose your coordinate system. And then once you have your coordinate system, write down all the forces on each particle in your system, on each particle. Draw a diagram. You have your particle, and we also draw all the forces that are acting on that particle. This is what sometimes people call drawing a free body diagram. So this is draw a free body diagram. Free body diagram. This describes the body, the particle, and all the forces that are applied to that object of interest, to the body, to the particle. And we will see examples of this in our modeling discussions in future videos. Now, that was a step one. So step one, choose your coordinate system, draw the free body diagrams, and then step two, apply the Newton's second law. Now that you know all the forces that are exerted on each particle, you can apply the Newton's second law. Second law, F equals ma. The total force on each particle is equal to the mass of the particle times the acceleration. And once you do this, this will give you the equation of motion. You construct the equation of motion. An equation whose unknown is the position, is the trajectory of your particle. To construct the equation of motion, the equation of motion. And finally, once you have your equation, you will solve the equation. 3, solve the equation, either using analytic techniques or numerical techniques. Numerical techniques are those techniques that provide approximate solutions. Solve the equation of motion. Equation of motion. We will see several examples of this in future videos. So this is the reason that I try to tell you a little bit of the process that we should follow in order to apply Newton's second law, and we will see this. We will see this in action very soon. So one source for the ODEs that we will see will be the fact that derivative with respect to time is rate of change. That is definitely one of the key sources behind ODEs, that some of the ODEs that we will see. Another a key source behind the ODEs that we see is this Newton's second law. Newton's second law will result in equations. These equations are in the form of differential equations, as we will see. And then let me talk about the third source. Another source behind many of the ODEs that appear in our modeling problems. And this third source is actually really important. It plays a key role in modeling real world, and it is what I will call conservation laws. So let me write this. Another source behind many of the ODEs that appear in modeling, real world problems, modeling real world phenomena, real world problems, is conservation laws. Conservation laws. Okay, so now the question is, what is a conservation law, right? That is a very legitimate question to ask. What do you mean by a conservation law? What is a conservation law? Conservation law. Let me try to explain a little bit what we mean by this. And of course, again, you will see this in action as we will do our specific modeling problems. A conservation law is essentially a verbal expression of a fundamental balance. Let me just be more concrete. Suppose we're interested in the amount of quantity A, some quantity A inside the box, inside the pipe, inside the box. For instance, think about you have you're interested in the amount of certain like salt inside the pipe, right? How much salt do we have inside the certain tank, inside a certain box? Right? A conservation law, a conservation law would state something like this, something like. So I'm gonna tell you what the conservation law would tell us, and you will see how natural it is. As in a little bit of thing, says that, oh, this is actually obvious. Obviously, this conservation law must hold. So what does the conservation law tell us about this situation? The situation that we have a box, we have a tank, it has the quantity, it has some substance A in it, and we are interested in the quantity, in the amount of quantity A inside our tank, inside our box. A conservation law would say the following. It would say the total change in the amount of quantity A from time t1 to time t2 must equal the amount of A, the amount of quantity A that enters the box, the tank, during that time, and then minus the amount of quantity A that leaves the box, the tank, the pipe during the same period. Do you agree with me that this makes perfect sense, right? So I have a like a box, I have a pipe, I have a tank, and this quantity A is here, and I'm interested in the change in the amount of quantity A from time t equals t1 to time t equals t2. So, and what this equality is telling me is that if you want to understand how much the quantity A changes, look at the amount of A that enters the pipe and the amount of A that leaves the box, right? The amount of A that enters the box minus the amount of A that leaves the box, that will be the change in the amount of A from T1 to T2. Of course, assuming that there is no creation or annihilation of A within the pipe, within the box. So it's under that assumption that there is no creation of the quantity A inside the box, there is no annihilation of the quantity A within the box, this equality should hold. Another way of saying the same thing, in a sense, is as follows. Or another way to state our conservation law is that, or we can say, the rate of change, the rate of a change of the quantity A, in the box, in the pipe, must equal the rate at which the rate at which the quantity A flows into the box, minus the rate at which the quantity flows outside the box, flows out of the box. The rate at which the quantity flows out of the box. Out of the box. And here, think of this term rate as amount per unit time. For now, think of it as amount per unit time. I will be more careful about this term very soon. So for now, think of rate. For now, think of rate. Think of rate, the term rate as amount per unit time. Amount per unit time. Unit time depends on the application. It can be 1 second, it can be 1 hour, it can be 1 day. And then what this equality, this conservation law is telling us is that the change in the quantity A in 1 unit time per unit time is equal to the amount of quantity A that enters the box per unit time minus the amount of A that leaves the box per unit time. Right? We will be more careful about this very soon. We will be more careful. We will be more careful about this term, about the interpretation of this term, the interpretation of this term very soon. Okay. So what we have learned so far is that we have multiple, like that we have talked about several sources of ODEs that we will encounter, including Newton's second law, including conservation laws. Again, the conservation law should make perfect sense. For example, for the conservation laws, consider the population of a certain animal species in a given region. And then the conservation law says that the rate of change of the animal population, must equal the rate at which animals migrate into the region minus the rate at which they migrate out. Of course, plus the birth rate minus the death rate. In a sense, in the case of animal population, we have creation and annihilation of the quantity within the region. Okay? So conservation laws should also make sense. And now I want to talk about another source behind there's many interesting ODEs that we see in modeling real life applications. So this will be item four. Another category of ODEs that we see in the study of real world problems are those that arise during the solution of partial differential equations, are those that appear as you're solving a partial differential equation, that appear during the solution of partial differential equations. So this is a topic that you will learn more about when you take a course on partial differential equations. It is the case that a variety of phenomena in real life, they are modeled by partial differential equations. Some of the fundamental laws of nature, from quantum mechanics to general relativity, the basic equations of partial differential equations. And it turns out that several interesting techniques that we have for solving partial differential equations. What they do is that they transform the partial differential equation that originally governs the physical phenomena of interest into a collection of ordinary differential equations. For instance, let me be more specific. For instance, there is a widely used, there is a widely used method for solving partial differential equations, for solving PDEs. Remember, PDEs are those equations where the unknown is a function of more than one variable. The Schrödinger equation in quantum mechanics is an example of a partial differential equation. Wave equation, which can be used to describe vibrations of a string, is a partial differential equation. Heat equation, which can be used to describe the temperature distribution along a rod, is a partial differential equation, and so on and so forth. So there is a widely used method for solving PDEs. PDEs, like our abbreviation for partial differential equations, called the method of separation of variables, the method of separation of variables of variables. And this method, what it does for us is that it essentially transforms the governing PDE into multiple ordinary differential equations. This method essentially transforms the problem of solving a PDE into the problem of solving multiple ODEs. And it is a fact that the collection of important ODEs that people need to deal with, those are ODEs that they come from this situation, that initially we were interested in a partial differential equation, and then the method that we were using for solving our partial differential equation, it transformed the partial differential equation into a collection of ODEs. And now we will have to develop methods for solving those ODEs. Again, let me be even more specific about this. For example, the famous Bessel's equation. And then it's one of the famous equations, ODEs, that people study in any serious introduction to ODEs. The famous Bessel's equation, which is an ODE of this form. Find a function y of x such that x squared y double prime plus xy prime plus x squared minus n squared. Here n is a fixed number, y equals 0, arises during the solution of a PDE that models the vibrations of a thin circular membrane. So the bottom line is that a collection of famous, interesting ODEs that one must definitely get familiar with if they want to claim that they know about ODEs. The way they appear is that initially we start with a partial differential equation that is supposedly describing a phenomenon, and then during the solution of the partial differential equation, we arrive at these ODEs. Here, for example, the example that I gave you is that you need to solve a wave equation, a partial differential equation about vibrations of a membrane, and then it will result in this ODE. At some point during the solution, you will arrive at this ODE. All right, and let me mention one more interesting source behind the ODEs that we may encounter, and this is also a very interesting thing to know. This will be our item five. Item five. Another source. Another source behind the ODEs, like a good portion of ODEs that we see in real life the modeling, in real world modeling, behind the ODEs that we see in real world applications, is the Euler-Lagrange equations, Lagrange equations that arise from optimizing a functional. If time permits, I will certainly create a video to give you more information about this category of ODEs. I will explain more carefully what we mean by functional and what we mean by Euler-Lagrange equation associated with a given functional. This is a topic that I need more time to explain more carefully, but I just wanted you to hear the terms here, right? There is like a class of interesting ODs that everyone who wants to claim that they know ODs, they should be familiar with, and this class of ODs, they stem from Euler-Lagrange equations, the minimizing certain functionals, and that is something that I will carefully discuss, hopefully, if time permits. And you will see how powerful this tool is, the Euler-Lagrange equations for minimizing functionals. And I will obviously explain the term functional, what we mean by the term functional here. All right, so what we did in this video is that I quickly went over some sources behind the ODEs that appear in real-world applications. This one source was the mere fact that we can interpret derivative as the rate of change. Another source was Newton's second law of motion. Another source was conservation laws. That should make sense. Another source was this idea that many times we model the real world phenomenon using partial differential equations, but as we are solving partial differential equations, we arrive at certain ODEs that we need to solve. And then finally, I told you that there is the interesting class of ODEs that they appear as Euler-Lagrange equations. I didn't give any further explanation. I will create a video. I will talk about more about Euler-Lagrange equations and why they are important.